So here we are with another key idea from our third lecture on motion in one dimension, or motion in a straight line. And the key idea that I want you to kind of get from this lecture is about the relationship between the three quantities: position, velocity, and acceleration. In this lecture in particular, we introduced the concept of acceleration. And we saw how it's related to velocity. And the usual way that we introduce this is to define acceleration as the rate of change. Let me change my notation just for a second. The rate of change of velocity with time. And this is the average acceleration. So again, just like we have with position, and velocity, we had that the velocity was the change in position divided by the change in time. And you remember from our previous key concept video, this is related to the concept of a rise over a run or a gradient. And so for some finite amount of time, delta t, our average acceleration can be found by basically taking the rise over run for our change in velocity. But obviously, as we take the limit, as delta t tends to 0, of this delta v over delta t, this is the definition of the derivative of the velocity with respect to time. And I should have a little line under there as well to signify that velocity is a vector quantity. So the key concept then is just essentially an extension of what we talked about in the key concept yesterday, which is how we can find an average acceleration as the finite difference or the change in velocity over the change in time, or we can find the instantaneous acceleration, which is the derivative of the velocity with respect to time. And so this leads us to a kind of chain of relationships. So we have that acceleration is equal to the rate of velocity with respect to time. But because we know that velocity is just the rate of change of position with respect to time, this is just d by dt of dx by dt. Because you'll recall that that's the definition of v. So we then have that this is d2x by dt squared. So we have this chain of relationships between acceleration, velocity, and position. And as we'll see in tomorrow's lecture, this actually leads us to a useful kind of sort of flow chart. If we think of position, velocity, and acceleration as our three key quantities concerning kinematic motion, what we actually measure is the position. Okay, we measure the position of something, a particle or a car or a person, a vehicle. And the rate of change of that position, so I'll signify that with a little d by dt here, gives us the velocity. Okay, how fast is this thing moving? Now, if we then take the rate of change of that quantity, so another little d by dt here, then we can calculate the acceleration. And as we began to see in today's lecture, we can then also think of this in the opposite direction. So if we take the integral with respect to time of our acceleration, we can compute the velocity. And if we take the integral with respect to time of our velocity, we can find the position. So understanding the way these three concepts are related to each other is really important. And that's because in most scenarios, what we actually measure about kinematic motion is the position. And from the position, we can then work out the velocity and acceleration. In most mechanical scenarios, we're actually measuring not the acceleration directly, but the forces. And if we measure forces, we can then work out what the acceleration will be. And from the acceleration, then we can calculate what the velocity and therefore the position will be. So this is really important, this relationship between these three things. And it's the key concept that I want you to grasp from the entirety of this week's lectures is the relationship between these three things.